So we have been talking so far about the features that we can see in a scanning electron microscope, and we said one of the features that we can observe is fracture. So we talked about how varieties of fractures appear. For example, a brittle fracture, a ductile fracture. In the previous class, we even talked about ductile fracture, which we called it as a dimpled fracture. So where whenever the fracture happens by a void formation and void coalescence. For example, if you take a ductile material and subject it to tensile forces, you will see that the material finally fractures with this kind of a feature, which people regularly call it as a cup and cone fracture, where the material slowly, as it gets distorted, and you will have certain voids that are created around some inclusions. If generally most of the materials have some inclusions, and whenever you have an inclusion inside a material, and the interface between these two gets separated out because of the forces that we are pulling, and that separation can cause certain voids around that, and these voids get created at a number of places, and all of them join together. And when you look at the surface of this, and that surface looks like dimples like this, like grains that we see, you see the dimples. Dimples are nothing but the crevices that are created because of the voids, and all these individual voids coalesce and then join together, and finally the material fractures. So, and if you carefully observe inside these particular voids, because of the depth of field that the SEM offers, you may be even able to see these inclusions which are contained inside this. And this is how we will be able to understand it is a dimpled fracture. Similarly, if you have a fatigue fracture usually, if you take a crankshaft which is rotating, and as a result you have both tension and compression forces alternately being exposed by this material, and such a material, usually the cracks initiate on the surface and the cracks start forming and then propagating, and because the cracks propagate in a fashion with this tension and compression loads continuously being experienced by the material, you would see a material when it fractures, wherever the crack is starting, you will see certain ripples kind of. Each cycle of rotation creates a ripple around this, and this crack propagates in a fashion like ripples in a sea, and this is what called beach marks. And the moment I see this kind of a feature, I immediately understand, yes, the material has failed by fracture caused by fatigue. So one can understand the nature of the forces causing such a failure. So whether a material has undergone fracture under tension or under fatigue or under impact can be easily seen. For example, if a material fractures like a brittle fashion, you will just see the material having what is called a cleavage fracture. For example, if you have ever seen a glass being broken into pieces, if you look at it, it will have a very smooth surface of the fracture, and that is what we call it as a cleavage fracture, because the crack has propagated very fast through the material, and such a crack propagation through the material would cause what is called a cleavage fracture, like a sheet of propagation of this particular crack, and can give you this kind of cleavage. Sometimes you can have a material with a partially ductile regions in the material and some brittle regions, and you can see what is called a quasi cleavage fracture also, which is basically partially cleavage and partially it could be dimpled, and these are all various features one can observe in a material. So this is one of the major applications of what we call it as the scanning electron microscope, and this particular field is called failure analysis, or people also use the term fractography. So that means you can analyze the failures. It is like a postmortem after the fracture has taken place. This is one of the limitations of this particular type of analysis, because the fracture has already taken place inside the material. So you cannot salvage it anymore. The material has already broken. But you can look at the material and understand why it has failed, so that in future you will be able to take care of the material in a better fashion, design the material in a better fashion, so that the future components would not undergo a similar failure. So that is how we can utilize this post-mortem kind of an examination, which is what we generally call it as a failure analysis, to understand this the nature of the fracture. And SEM is a method which is very, I would say, popularly used for the understanding of such failures. So this is one of the major applications of the scanning electron microscope. So with this, we will look at other microscopic techniques. We have understood now what a scanning electron microscope is, and we have also mentioned in one of the classes earlier that other than secondary electron image, we also have what is called backscattered electrons. I have mentioned this in one of the last classes, where you say that when you have electron beam falling on the sample and getting reflected, the electrons which are coming from the top surface are the ones which have very high energy, because they have not lost most of their energy, and these energies can be used to get an idea of what is called the electron density distribution inside on your surface. If your sample is a polished surface, let us say, for you to be effectively use the backscattered electrons, you have to have a polished surface. I cannot take a fractured surface and get a backscattered image, because in a fractured surface you have hills and valleys inside the material, and that will not be able to give you information about these electron density distribution. For example, if I have a sample with an aluminum copper alloy, let us say, again go back to the same example. So we have, let us say, precipitates inside the material. You have certain grains, and inside the grain there are certain precipitates. And I know that this precipitate is a Al2Cu, and this matrix is alpha. So alpha is mostly aluminum, and Al2Cu has almost 55.8%, approximately about 55.8% of copper in it. And so as a result, this particular region has more copper, and because copper has a higher atomic number, this particular region has a larger electron density per unit volume when compared to this region. So when an electron beam is interacting with this region, the number of electrons present in this region being more per unit volume when compared to this, so the scattering of that electron beam with this will be more. And when you are looking at the scattered electrons, because you are only collecting the scattered electrons, that particular region looks brighter when compared to the rest of the region. So you will be able to know that all those regions which are looking brighter in your image, in a backscattered electron image, will be those regions which have more atomic number. So if you have a material with elements having different atomic numbers, for example, this kind of a case, aluminum copper, you will be able to differentiate them. So this is a qualitative way, I would say. Definitely not a quantitative way, because I first of all do not know what element is that. I would also not know how much of that element is present. But I will be able to tell that yes, there is a elemental distribution inside this, and we can go to the next level, called what is called elemental mapping can be done. We will come to that a little later, using a technique called EDS or WDS, energy dispersive spectroscopy or wavelength dispersive spectroscopy. We can actually do elemental mapping. For example, if I do copper mapping, you will clearly see that everywhere else, wherever the Al2Cu is not there, there will be no copper at all. Okay, so the copper mapping, if I do, this whole region will look dark, and only these regions will look bright, because these are the regions where copper is there. So that is how I can find out, yes, the copper is distributed here. And if I do aluminum mapping, you will see, because the aluminum content of these regions is lower than the aluminum content of the rest of the region, because this is only having about 45% of aluminum, whereas the rest of it, this is almost like 100% of aluminum. I will be able to see that aluminum this region will have a lower intensity of aluminum, and these regions will have a higher intensity of aluminum, and I can make out that this is nothing but a phase with a lower aluminum content and a higher copper content, whereas the other phase is having a higher aluminum content and a lower copper content. But this is again only a qualitative. So mappings are useful to know how elements are distributed, but they give you only qualitative information. We will slowly see how to get quantitative information as we go along. So backscattered imaging is very useful, but if you want to have a backscattered imaging, the sample has to be well polished. And if it has a lot of roughness on the surface, it will not be able to give you a good backscattered image. So whereas for a secondary electron image, you are not bothered about what is the roughness of the surface. So even a fractured surface can be put and you can see the fractured features. But there my interest is not to look at what are the phases present. So if I want to get a phase contrast, okay, a contrast of what are the various phases that are present, I should go to backscattered image for getting a qualitative information. So these are the various features that we can get in scanning electron microscope. Now let's look at a few other microscopes which have become very popular. One such microscope which has become extremely popular much before even any one of these TEMs have come is what is called a field ion microscope. It has been transformed into what is called atom probe in recent times. People originally used to call it as a 3D AP, three-dimensional atom probe. Nowadays simply people call it as atom probe, or even they call it as atom probe tomography. The T stands for tomography, because you are seeing a three-dimensional information of how atoms are distributed. And this has started with a technique called field ion microscopy. In a field ion microscopy, what you do is you take your sample in the form of a tip, a tapered a sample like this exactly. You have a rod-like sample with a tip, and this tip has to be polished carefully in such a way that the tip radius is not more than about 100 nanometers. So it has to be specially polished. There are techniques to polish this. For example, one of the common technique that is used is what is called electropolishing. What you do is you have, let's say, this sample which is converted, which is stuck to a, let's say, an electrode, and make this as a positive, and then dip, let's say, a platinum ring into an electrolyte, so that you have a thin film of the electrolyte in it, and keep this thin film of electrolyte here, and then have a mechanism by which this particular needle is sent into the thin film and brought out. Okay, so when you keep on having, on an optical microscope, we have a way to move our sample. So if you fix this on the optical microscope so that you can move this thing and then keep this stationary, and so that this particular needle goes into and comes out, and in the process it keeps on getting dissolved, because this is made positive and this is made negative, and as a result the same kind of jet polishing that we talked about, electropolishing in case of TEM, a similar polishing can happen, and you keep this whole thing into an optical microscope so that you keep on observing using an objective lens and a eyepiece, and this is what we call it as a stereo microscope. That means you are trying to understand the 3D information of this, so that as you start observing, you may be starting like a rod of sample. You might start with a rod of sample, and as this rod is put into this electrolyte again and again as a function of time, you will slowly see that the tip starts, because whenever you take a rod, it is these regions which are the high energy regions. Okay, the tips, the corners, and the corners start getting blunted, and slowly the dissolution happens, and finally the sample becomes like a tip like this. And once you observe that it has formed a tip, of course your the resolution of this microscope is not good enough to be able to actually see that whether it is 100 nanometers or not. But as long as you feel that it has become a tapered sample, then you put it into an electron microscope for TEM, and make sure that yes, it has of this particular order of curvature, and then put it into a field ion microscope. And once you put it into a field ion microscope, what you do is you keep this into a chamber which is highly evacuated, and you fill this with a small amount of helium. It is evacuated up to 10 to the power minus 10 torr, so that there are no gas molecules inside, and then you fill this with a helium, and once you make your sample which tries to attract these helium atoms and get these helium atoms get deposited on the surface of this, because the surface is having a very high energy because of very high curvature, and as a result you can basically view this particular thing using a kind of imaging plate, where you basically see the image of this particular surface using microscopic features, and that is how you can see how the tip of the sample is. For example, how the atomic arrangement of the tip. For example, if it is a BCC structure and if the tip is having a particular atomic plane, let's say 110 plane, you will be able to observe how the atoms are arranged on the tip. So this particular microscope was originally used to see atomic resolutions on the surface. For example, if it is a particular material with a particular structure, whether it is FCC or BCC or HCP, all these atomic arrangements, and if there are certain defects, let's say there is a dislocation, you will be able to see easily on the surface. But this was only used to visualize only surface crystal atomic arrangements. Okay, so whenever you are interested on how the surface atomic structure is, you may ask me, why are we bothered about it? We are bothered about it whenever you want to use for any material for catalysis. A catalyst, the surface is the most important thing. How is the surface structure? It determines how active the catalyst is. So I need to know the surface structure, prepare the surface with a particular atomic arrangement, so that I will be able to get the best type of a catalyst. So people used to use this particularly to look at such surfaces and get to know what is the surface arrangement. If the surface arrangement is what we want, is of a particular nature, prepare the surface accordingly, and so that you will be able to get that information. But later what people thought was, just knowing surface information may not give me all the information. Can I know how the atoms are arranged in 3D inside the material? Particularly, let's say if I have a grain boundary here inside this material, I want to know what kind of an atomic arrangement. For example, if I have a grain boundary passing through a material like this, if this is a material with such grain boundaries, and I have a small precipitate here, and I want to know how the atomic distribution is, then what people started doing is, they started applying a pulsed voltage on this tip with about around 20 kV or so. And when you use such a pulsed voltage on the tip, then what you do basically, you sputter away the atoms from the surface, and when you sputter away the atoms from the surface, these atoms will travel towards a detector, and these atoms, when they reach the detector, you can find out from the time that it has taken to reach the detector, you can find out what particular that element it is. This is what we usually call it as mass spectroscopy. So using these principles of mass spectroscopy, you will be able to know what atoms are reaching, and layer by layer, if you can sputter away and accumulate all these layers, and you will be able to know in 3 dimensions how the particular material has atomic arrangements. So you can get a complete atomic arrangement distribution inside a material. Of course, the limitation is we do not see sample sizes more than about a micron. This, I would say, possibly is the largest size that we see. So most of the depths that we see are on the order of around 100 nanometers to about 500 nanometers. This is the kind of range that we see, because as you want to collect more and more atoms, obviously each layer has to be evaporated, and each layer you have to wait until all the atoms are collected, because you do not know whether that particular layer has a small atomic number atom or a big atomic number atom at the moment. So the detector waits until all the atoms come, and until no atom is being added within a certain particular period or so, then it says, okay, fine, now let's go to the next. Because we know what is the time taken for each of the atoms. For example, if there is boron inside the material, and we know its atomic number, and for that particular atomic number, what is the time it takes for it to travel a certain distance x is known. So knowing whatever is the smallest atomic number that I would like to detect, you can wait until that particular time, and if no atom joins, so that means that particular element is not there, so you can start with the second pulse. So one by one, layer by layer, pulses are given like that, and it is allowed to. And as you give a pulse, one layer has gone, so as a result the distance has changed. So you have to recalculate the whole thing and be able to find out again the times to be calculated with respect to the distance. So the distance has to be accurately found out, and that is how we will be able to do it. And because it takes a very long time, people do not usually go to very large distances. In fact, I should say the older atom probes, which are called 3D APs, used to take for collecting an information of a 200 to 500 nanometer depth would take at least about 2 days for most of the metals. Whereas nowadays we have a new technique called LEAP. It is called local electrode atom probe. In this local electrode atom probe, the configuration of the machine is such that you can accumulate atoms at a very fast rate. So usually people collect a rate of atoms almost like 3 million atoms per an hour. So it's a very fast rate, and similar depths can be accumulated even within a few hours by a leap. So this is a very fascinating technique which is used particularly to understand the elemental distributions. It is not a microscope as such, but it is more like a spectroscope, but it can give you atomic distribution in microstructural features. If my interest is to look at how the elements are distributed at grain boundaries, for example, nowadays people are talking about grain boundary engineering. So you would like to know what is there at the grain boundary to be able to understand. Even, for example, in thin films, I am interested to know what is there at the interface between any two thin film layers. In case of multi-layers, semiconductor electronics, for example, if I am putting a gallium arsenide onto something else, I want to see how is the interface between them. Is there any segregation? Is there any reaction product at the interface which might influence my properties, functional properties? I need to look at that. So people look at all these things in a greater detail to be able to understand the elemental distribution and finally correlate it to the properties of the material. So this has been a wonderful technique which is an ultimate tool to be able to find out the atomic distribution. And this is a 3D information. Please remember, all the techniques that we have talked so far, whether it is a TEM or an SEM or even an optical microscope, these are all 2D informations. We are not talked about 3D in this, whereas atom probe is a technique where you can truly get a 3D information about the sample. Of course, you have to have the proper, what I would say, patience to wait for all the atoms to be accumulated and be able to get. And at the same time, one also has to remember that you are only looking at smaller regions and imagining that the smaller region is representing the whole sample. That is one of the major limitations, and that limitation is there even with the TEM, because even in a TEM, what you are seeing is a few microns region, and imagining that this few microns region is representing the whole sample. So that is one limitation. As you go to higher and higher resolution microscopes, you are actually seeing smaller and smaller regions. When compared to an optical microscope, you go to a SEM or you go to a TEM, actually your area of view keeps on decreasing as you go from one to the other. So as your area of view is decreasing, as a result, you are actually seeing a smaller region and imagining that that is representing the whole sample. So this limitation is always there, and that's the reason why many people prefer a SEM rather than a TEM, because in SEM I can see a large region. So that is one of the things. Even in a TEM, though I might start with a 3 mm disc, if this is a 3 mm disc, with a 100 micron sample, 100 micron thickness. If this is my starting material, when I do jet polishing, finally what I am looking at is a sample like this, and what I am looking at is only a region around this. A hole has formed here, and I am looking at a region around this hole. So though my actual sample is 3 millimeter, what I am seeing is a small region around this hole where the tapering is such that the thickness of the sample is approximately about 100 nanometers. So what I am actually confining myself is to around a maximum of around 2 to 5 micron square kind of a region. I am not seeing anything bigger than that. So the region that I am looking at, and it again depends on how well you have polished your sample. If you have been able to polish your sample well, such that the thinner region extends over larger distances. That is why in when I am doing iron milling, depending on what is the angle, if I have this sample and an iron beam is falling, if the iron beam falls like this, then it will simply make a hole through the sample. So it will not thin the material. So if an iron beam falls at a very glancing angle, so it is actually removing the sample surface atoms. So it creates a much shallower depths, and as a result, the larger regions will have thin regions. So most of the time, that is why people can control this angle at which the iron beam falls. So they start with a large angle, so that it actually initially removes the atoms, sputters away at a much faster rate, then slowly change the angle such that it becomes like a glancing angle towards the end, so that you create a large region which is a thin region. So our objective in all this polishing technique is to have as large a region that I would like to visualize. But that region should have a thickness of this, and that's the region only that I can observe in a TEM. So as a result, if I can have a larger region with a thickness of this, then that's the best condition. So, and that is what people would like to achieve, and people have been doing that. But in case of an SEM, you are not limited by that, because there is no sample preparation specially required except in polishing your sample. So in principle, if you are putting a 3 millimeter sample, you can actually see the whole 3 millimeter sample. In a TEM, you are not actually seeing, though you are starting with a 3 millimeter disc, you are not seeing the whole 3 millimeter. Whereas here, even if I put a 1 inch sample, I actually see the whole 1 inch sample. So that is one plus point of an SEM. You are able to see a larger regions and can make out from that whether the sample has a homogeneous microstructure or inhomogeneous microstructure, and will be able to talk more about the overall sample characteristics, whereas here you are limited by a small region and projecting from there that this is representing the whole sample, which may not be always true. So this is certain advantages of scanning electron microscope when compared to transmission electron microscope. Now let's look at one more technique which has become very popular, which is called scanning probe microscopy. This is a microscope like an SEM. It scans the surface, and as a result, it is giving you information about the surface characteristics of the sample. In principle, it gives you surface topography. But unlike the SEM, it can give you topography at the atomic level, because I am using a probe and trying to look at the probe material interaction by bringing the probe as close to the surface as possible. And there are different techniques that come under this particular broad category of scanning probe microscopy. The two most popular techniques are what is called STM, scanning tunneling microscope, and the second one is called AFM, atomic force microscope. So these are the two very popular, and they come under the scanning probe microscope. Scanning probe microscopy is a general term which is used for all microscopes where you use a probe, which is basically a cantilever, which moves on the surface in a line and then covers the whole surface in a number of steps. So you can take a sample, put a probe on it. A probe can look like this, a cantilever like this, and this probe is kept on the surface of the sample and allowed to move in this direction, in this direction. And once it moves in a particular x direction like this, and then you can move it further by another y direction. Again allow it to scan like this. Again you can allow it to scan like this. Like this, if you keep on doing it, you will be able to cover the whole sample. So, and while covering the whole sample, you will be able to see how the features of the surface are by looking at how this probe interacts with the sample. And this probe surface interaction is what is measured in case of a scanning probe microscopy. And one of them uses a principle of tunneling. What is this tunneling? We know that whenever two conducting samples come very close to each other, the electrons tunnel through this. And this, in fact, this is one of the major problems that people talk about nowadays with the new electronics, where we are trying to increase the density of transistors in a small region. For example, if we are now talking about terahertz memories, and then people talk about terabyte capacities of the most of the computers. Whenever you want to have such a high speeds, you would like to have this performed by a large number of transistors pumped into a small area. And when you have a large number of transistors put into a small area, obviously the distance between the transistors comes down, because the density of the number of transistors increases. And when the distance comes down, you come to a limit where there is a tunneling, and there is some kind of a short circuiting taking place between the two transistors. So because the distance between the two is too small, that you reach such a limit of tunneling, and people say that is a theoretical limit to which you can reach. So nowadays people believe that with the 20 nanometer transistor that is already available, and people say that if you go further down to 10 or below 10 and put a large number of them into a smaller area, you would see that you are already reaching that limit. So people are now looking at newer techniques. For example, there is something called SET, which has become more popular now, which is called single electron transistors. One electron acting as an on-off switch is another technique where a lot of people are going into, so that you come out of this transistor technology and use other technologies where you can somehow overcome this tunneling problem. Whereas here we use this tunneling as a tool to understand the surface features. For example, if I can take a material, with an atomic structure, for example, if I can look at, let's say, an atomic arrangement like this on the surface. This is, let us say, your surface of your material. This is your surface, and in which you have atomic arrangement like this, let us say. Now your probe is moving on this. You have a probe which is moving on this surface. So the moment this probe comes to this region, because this is an atom containing certain number of electrons, there is a certain electron density there, and as a result, if this tip is close to this, there can be a tunneling that can happen between these two. And the moment the beam, the cantilever comes to this region, because you are maintaining the distance, you see here the electron density is smaller. So as a result, it feels that there are less number of electrons, and as a result, you will not see any tunneling taking place. And hence, you will, when you try to collect this information and try to image this using the electrons that are being, what I would say, are being exchanged between the tip and the sample, you would see that this region suddenly looks black in region, whereas this region looks bright. So you will be able to see an information which gives you an idea of that there are certain atoms which are periodically arranged with a certain distance between them. And this particular exchange also depends on which atoms are present there. So for example, if you have an alloy with aluminum and boron in it or something like that, you will be able to see one atom is boron, let us say, another atom is aluminum. So the number of electrons here and the number of electrons here are different. So you will be able to see some contrast difference. And from that, you will be able to see which element is distributed in what fashion, whether it is there is a cubic way of arrangement or some other way of arrangement, will be able to be seen by simply measuring the tunneling current. But one important thing that we need to understand is this can happen at a very, very small distances. And that basically puts a demand on the sample that the surface has to be extremely smooth. If the surface is not very smooth, the surface roughness alone can cause noise in the whole spectrum that you get or in the whole image that you get. So as a result, the surface has to be extremely polished and the tip has to have extremely fine radius. In principle, the tip has to be 1 atom kind of a tip. So that is the level of preparation of the tip that is important. So what we talked earlier, to prepare a sample for a field ion microscope, similar preparations have to happen. And people nowadays not only use this kind of chemical preparation, electrochemical preparation, there are also other techniques that are available, which is now popularly called as FIB, what is called focused ion beam. What I do is, if I have a sample which is like a rod, I want to make it into a tip like this. So what I can do is, I can use an ion beam and focus that ion beam on the surface and then sputter away the atoms slowly, as if I am milling away, doing like a lathe machine, where I take out the surface of the sample and make the sample of a particular shape. Similarly, I can do that milling on my surface so that finally I make it into a tip like this. So focused ion beam is very popularly used nowadays to be able to do this, because electropolishing has problems in the sense, if my material is a reactive material, when I am doing electropolishing, it can get oxidized. For example, if I am working with a titanium alloy as a zirconium alloy, there is a possibility that it gets oxidized. So surface may be coated with an oxide layer, and that can cause a lot of problem in visualizing. So in order to do that, so what we do is, we put this sample into a chamber which is evacuated, and then put argon ions into it, ionize that, and then make it into a beam, and then like an ion milling which we do for a TEM sample preparation, similarly such a thing can be used, where I focus the ions and then get the prepare the sample. So usually FIB is used for preparing the STM tips or AFM tips, or even for the tips that are required, or samples that are required for 3D AP or atom probe tomography. So this is very common nowadays. Even for scanning electron microscope also, if you want to have observe a multi-layers in a sample, let's say you have multi-layers of certain electronic packaged material, and you can actually slice that using a focused ion beam and see what is there at various interfaces. So FIB is one of the I would say sample preparation techniques which is regularly used along with any one of these microscopes nowadays, and it has become like a part and parcel of all microscopy equipment. So once you prepare such a sample, and once you prepare such a probe, and you use that probe and be able to get an information of this. Not only you can get information on the surface at the atomic level. Interestingly, if you see carefully, so far we have said the resolution depends on lambda. If you look at all the microscopes that we talked about, optical microscope, our own eye as a microscope, if you want to call it as, and then we talked about scanning electron microscope, transmission electron microscope. In all these things, we define the resolution in terms of lambda, and we said usually the resolution is lambda by 2. And here what you have is a sample where you have a surface polished, similar to what you would have polished in an optical microscope or something like that, and a tip, and the whole thing is in principle in either air or a very fine vacuum. But there is no waves that I am using, and there is no radiation that I am using here to be able to visualize the surface and get a high resolution. So here the resolution concept is entirely a different concept, where it is not limited by the lambda. And as a result, you are able to get an atomic resolution by simply using the what is called the interaction of the probe with the surface. So it is the forces between the probe and the surface is what I am trying to observe. And for that, I bring this probe very close to the surface. Only when you bring it very, very close to the surface, then only the forces become predominant. Otherwise, the forces are not predominant. So that is a technique which I use to get a atomic level resolution. So you get a similar atomic level resolution that I would have possibly get in a high resolution transmission electron microscope, where I am able to see atoms, or in an atom probe tomography where I am able to see atoms. Even if you look at atom probe tomography also, there is no lambda limitation in an atom probe tomography, where I am only sputtering away atoms and collecting the atoms atom by atom and being able to see them. So you can see that these are techniques which are not lambda limited, whereas optical microscope, SCM, TEM, these are all lambda limited, and also they are limited by the aberrations, obviously. So here we don't have such problem of the aberrations. Of course, the question is this particular energy or the electron transfer that is happening, the tunneling that is happening, how do I measure it? Is a question. Okay, this measurement, the measuring tools that I am using to measure this should be as sensitive as possible. Otherwise, I am not able to see the differences between these two. Particularly if I have an aluminum and a silicon, I want to see the difference. The atomic number difference between these two is very small, and as a result, the number of electrons difference between these two is very small. So as a result, unless my measuring tool is very, very sensitive, which are basically piezoelectric materials which are used to measure those electrons that are coming, which can cause certain differences in terms of the expansion or contraction of the material, and that expansion or contraction is what you are actually measuring in terms of the differences in the electron densities. And as a result, one has to be very, very careful in choosing the tools to give you. So the whole resolution in terms of atomic number resolution depends on the sensitivity of the tool that you are using to measure these electron differences. So this is how one can use a scanning electron tunneling microscope to be able to see the surface topography of a sample. Not only see surface topography, people also use it for actually manipulating the surfaces. People have gone to the extent of, for example, if you have a surface on which you have atoms, people are able to use this scanning tunneling microscope to bring a tip very close to the surface, and when it comes very close to the surface, it can actually pull out this atom from that surface by the force of attraction between the tip and this atom, and then lift the atom and put it on some other surface. So this is a technique which is regularly being used, and if you go to Google and look at various interesting images that can be created, people have created letters, various characters and things like that. For example, they create, let's say, atoms, put something like this, and then create things like this, various letters, so which are nothing but atoms being put in a particular fashion, so that you will be able to create various images that are of interest to you. So people have done all this, and this has become very popular, and in fact that is one of the reasons why scanning tunneling microscopy has become very popular, that you can manipulate atoms. In fact, if you remember long back when Feynman gave his lecture in 1959, he said, I should be able to manipulate atoms the way I want. That was one of his famous statements, that I should be not only able to see the atoms, be able to manipulate. And this has been done for the first time in 1990 by the people using the scanning tunneling microscopy. And possibly you are aware that scanning tunneling microscope has been invented for the first time in 1981. And in 1986, it has been given a Nobel Prize for the two people who have done this, Binning and Rohrer. These are the two people who have done, and that is when, along with this scanning tunneling microscope, people have also given a Nobel Prize to von Raska for his invention of the TEM. So you can see the scanning tunneling microscope is a fascinating tool which can not only image the surfaces, can also create features using this. And so you are able to use this kind of fine forces between a probe and the atoms, and utilize those forces, and even can lift atoms and manipulate these atoms to various structures. So this is one of the techniques which has become very popular, and people use this very regularly, and they call this particular new technique of manipulating as what is called nanolithography, because you are writing. Lithography is a technique where you can use to write things. So because you are using this technique to write things, or drill small holes if you want, or create different structures that you want, and people call this as a lithography technique, and to be able to do this kind of things. So variety of structures have been found by this. The second technique in this group of techniques is what we call it as atom force microscopy, which is called AFM. AFM is similar to scanning tunneling microscopy, but we don't use the tunneling concept here. We only use the forces that are there on the surface and this, the tip that we have, and measure these forces. And these forces obviously depend on whether I am close to the surface or far from surface. The farther I am from the surface, the weak the forces are. So if you want to really be able to measure the forces and be able to see strong forces, you have to bring the tip very close. And in this, there are two types of modes in which this AFM is used. One is called contact mode, another is called tapping mode or non-contact mode. Contact mode is where the tip is actually allowed to touch the surface, and it moves on the surface. And when it moves on the surface, as I mentioned, the moment you have atoms on the surface, the moment it moves on the surface, it actually can see the configuration of atoms. When it is moving on the surface, the moment it moves between the two atoms, it sees that there is a depth there. And because the force between the tip and the atom changes from atom between two atoms when it comes to a region where the atom is not there. So this is something which people are able to see and be able to get information about these forces and use this information to understand the microstructural features of the surface. I think we will stop here and then take it up in the next class.